The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Now, signal detection is not solely based on the strength of the signal. Now, what do we mean by that? If we take a look here, as you might expect, individuals differ in their ability to detect stimuli. Thus, there's no single fixed value above which an individual will always detect a stimuli, or below a fixed value in which an individual will never detect the stimuli. This is where signal detection theory comes in, and it abandons the idea of a threshold. Rather, it involves treating the detection of a stimuli as a decision-making process. That is, the nature of the stimuli, sensitivity one has to the stimuli, and cognitive factors all need to be considered in this process. Let's take a look at an example and a definition now on the next slide. If we take a look here now at figure 9, have you ever missed a phone call simply because you did not hear it or heard the doorbell ring only to realize in actuality that it didn't? This is best explained by signal detection theory, which states that the response to a stimulus depends both on an individual's sensitivity to the stimulus in the presence of noise and on a person's decision criterion. Now, that being our experiences, expectations, motivations, alerts, and costs and gains of being correct or incorrect. When stimuli are difficult to detect, cognitive factors are critical in the decision-making process for an observer. Furthermore, it's also important to note that decision-making takes place in the presence of some uncertainty. In short, there is a cognitive decision-making element that needs to be considered. Moving along, individuals set their own decision criterion, that is, a benchmark of how certain they are a stimulus is present before stating they detect it. And the decision criterion for an individual can change. We've already listed some of the factors that can affect the decision criterion, right? That being our experiences, expectations, motivations, alertness, and costs and gains of being correct or incorrect. Next, let's take a look at a typical sensory experiment, but before we proceed, let's get a better understanding of what noise is. Noise refers to all other stimuli that comes from the internal and external environment. Moreover, external noise refers to environmental factors such as sights, sounds, smells, etc. that compete for your attention. And similarly, internal noise would be your motives, memories, or frame of mind entangled with what you're seeing, hearing, or smelling at any given point. Thus, the internal noise contends with an individual's ability to detect a stimulus with perfect uninterrupted attention. Next, let's take a look at a typical signal detection experiment. Signal detection theory, in the presence of noise, measures an observer's sensitivity to a stimuli and decision criterion separately by randomly presenting a stimuli on some trials while omitting it from others. Let's use the signal detection outcome matrix here to demonstrate our point and illustrate the 4 possible outcomes from a signal detection experiment. When an observer is presented with a faint stimulus, they can provide one of 2 responses, that being the signal is present or the signal is absent. If the stimulus is presented and the observer responds yes, it's called a hit. If the stimulus is presented and the observer responds no, it's called a miss. Conversely, if the stimulus is absent and the observer responds no, it's called a correct rejection. If the stimulus is absent and the observer responds yes, it's called a false alarm. Moving on, in signal detection theory, we can use the number of hits relative to the number of false alarms to measure the degree to which an observer's performance is due to their sensitivity to the stimuli or their decision criterion. If we zoom out a bit here, let's consider how the results differ between observer A and observer B if they only differ in their criterion level, that being their decision criterion. beginning with observer A, who has a liberal criterion, meaning they're more likely to give a yes response whenever there is any suspicion of a stimulus. If we come over here, if observer A is more likely to give a yes response, this will result in few misses, but also numerous false alarms. Conversely, if we consider observer B, who has a conservative criterion, this means that they're going to be more likely to give a no response and answer yes only in cases when the stimulus is easily recognized. Then if we come back over here, this is going to reduce the rates of both hits and false alarms. Additionally, we should also note, even when the two observers differ in their criterion levels, such as observer A and observer B do, it is possible for both observers to be equally correct in detecting the presence or absence of a stimulus. Moving on, let's now consider how the results will differ between observer A and observer B if, in addition to the criterion level, they also differ in their sensitivity to the stimuli. Thus, we'll now consider observer A to have a liberal criterion and a low sensitivity to the stimuli, whereas observer B will have a conservative criterion and a high sensitivity to the stimuli. In this scenario, if we come over here, observer A with a liberal criterion and a low sensitivity is more likely to respond with a high rate of false alarms relative to hits, whereas observer B with a conservative criterion and a high sensitivity is more likely to respond with a high number of hits relative to false alarms. Okay, great. On a separate note, it's also possible for researchers to influence the response of observers. This can be done by manipulating the costs and gains in giving correct or incorrect responses. For example, if a hit is rewarded more positively than the other three responses, then as you might expect, the false alarm rate will also be higher. Now, what do you think would happen if a correct rejection response is rewarded more positively? If a correct rejection response is rewarded more positively than the other three responses, then hit and false alarm rates would both decline. In short, signal detection theory looks to understand why individuals with very similar sensitivity respond differently to the same stimuli, and why an individual's reactions differ as the circumstances change. Next, let's take a look at a basics example that utilizes the matrix and also involves the decision criterion. Take a look here, and we'll begin here with figure 11 and figure 12. Say we're in our car, and while we're driving, we think we hear a possible clunking noise coming from the engine. However, due to the external noise, that being the sound from your speakers and other sounds coming from the road and your environment, you aren't completely sure that the sound came from your car. Now, if your car is relatively brand new with no history of breaking down, you may decide to ignore the noise by telling yourself that you just misheard the sound. Alternatively, if you look here at figure 12, if it's an older, unreliable car that has a severe history of breaking down, you may decide that the possible clunking noise you heard did come from the engine, and you decide to take your car to the next mechanic shop you see. Next, let's use the signal detection theory in this scenario to lay out the cognitive decision-making element. If we take a look here at the matrix, there are four possible outcomes, that being a hit, false alarm, miss, or correct rejection. Let's put the matrix into context with our example. If we zoom in a bit here, the signal or stimulus is the clunking noise. The participant's response is whether or not you heard the clunking noise coming from the engine. We have two cases where the correct response is given and your decision leads to a positive result that is beneficial, that being the hit and correct rejection. Or additionally, we also have two cases where the incorrect response is given, and as you see here, your decision leads to a negative result that is costly, that being a miss and false alarm. Next, let's shift our attention towards graphical interpretation of signal detection theory. And we'll begin by examining probability of occurrence curves. If we take a look